So for those of you who I don't know, my name is Marynel Vázquez. I'm an assistant professor at the computer science department at Yale, where I lead the interactive machines group. And what we generally work on is human-robot interaction. Now, what is human-robot interaction? Well, I would say these pictures probably summarize a lot of what we normally think of, right? We want robots to be able to engage with users in a variety of scenarios, perhaps to help, senior people with keeping them active, help kids with learning new skills, help people in the workplace, like you see in the top right, or maybe even help us create art, like you see in the bottom right with a robot by Autodesk. Now, oftentimes the world does not quite look like these pictures. Sometimes it looks more like this. And so there's not just one user that a robot needs to take care of or deal with. There's actually a lot of people around. And so this is exactly what we like to think of. How can we enable robots to operate in complex social settings with and around multiple people? Now, to make a little bit more concrete the challenges that come along, I'm going to show you a couple of different videos that hopefully contextualize this problem in practice. So again, think about robots in a variety of scenarios. One of the main challenges that happens here from a perception perspective is that, well, the more people you have around, oftentimes the more noisy and incomplete sensor data is going to be, which of course is going to make perception more difficult. Now, a second challenge that happens in these scenarios is that the more people you have, the more dynamic human behavior can be. So it's not just about raw sensing, but also about the diversity of the behaviors that you might observe here and there. And to show you an example, this is a video from an interaction that I did during my PhD at Carnegie Mellon in collaboration with Disney Research. The idea was very simple. We had this robot down below that was in our lab environment, waiting for children to come around to give them a souvenir in return for having come to our lab to test a couple of different technologies. And at this point, the kids had already gotten their souvenir, which is this piece of paper that they're carrying in their hands. But interesting things were happening. So, we as the roboticists, we expected these children to be all excited about the robot and just engage with it the whole time. But what happened was that not all of them did. So, for example, this kid that you see here in the top left, he had gotten his souvenir. He was definitely interested in the robot, but he was just not willing to engage with it as we definitely were expecting. Now, this was okay, right? Because the conversation with the robot could continue as long as there were other people interacting with it. And this is something that was afforded by the fact that there were multiple people in the environment. Now, another challenge that comes along with having multiple people around is that, well, no matter what you do, robots are going to influence people. And one of the best examples that I have of this is this art installation by Madeline Gannon. So here what you have is this very big robot manipulator right in the middle of this space. And the robot is kind of moving semi-randomly a little bit towards people, and that's all it's doing. Now, in contrast, this results in all sorts of, responses from people, despite the manipulator being rather simple. And so, given these challenges, how can we advance human-robot interaction for these multi-party settings? Our belief is that we need to take an interdisciplinary approach and think about not only sort of the technology side, about computer science and robotics, but also think about people, think about how we're designing technologies for the particular context where we're testing them. And so this oftentimes leads us to work in many different directions, from human-robot communication to understanding social group phenomena in robotics to perception and decision-making. Now, I don't have time to go, over many different examples. And so what I'll do is I'll narrow down my presentation to discuss efforts that we've done in the context of advancing understanding of spatial behavior in human-robot interaction. And here, what I want you to focus on is spatial reasoning for social robots. Hopefully, this will give you an overview of different aspects that you can bring together for this problem. Now, if you think about social robots and spatial reasoning, perhaps the first type of applications that come along are applications related to mobility, right? We want robots in general, if possible, to navigate around human environments to complete many different tasks, like, say, delivery. Now, oftentimes, we also want to combine this mobility capability with communication capacities that we want the robot to have. So, for instance, if I wanted the robot to go from one place to another, perhaps I want the robot to be able to understand a natural language instruction that describes the type of path that it's going to take. Now, if you have that robot navigating in human environments, not only you care about the actual motion of the robot, but you also care about social interactions that may be happening nearby. And these interactions may not look like it, but there's actually communicating a lot of other information. As we'll see later, spatial formations may tell you about who's interacting with whom in an environment. And so this capability of moving around and understanding interactions, they probably seem very disconnected at this point. But I'd argue that there's structure in these problems that could perhaps bring them together. And so let me make this more explicit. When you think about mobility, one thing that you normally care about is, well, places, right? That's your core reasoning unit. But you not only care about places in isolation, you care about places in relation to other places, because, perhaps you want to know, can the robot traverse from here to there, or what kind of motion should it execute to get to that other place? Similarly, in the context of interactions, you have a core reasoning unit, which are social agents. And not only you care about social agents in isolation, but you care about their relationships. Perhaps you care about relationships in terms of proxemics, which is how people reason about space in human environments, or perhaps you care about group membership, like I was describing before. And so if you think about these problems from this perspective, it's natural to start thinking about graph abstractions as a suitable way to represent information for these problems. And indeed, people have proposed topological maps and social networks to think about mobility and interactions in these types of problems. And so that's the key idea here. Perhaps it is, graph abstraction is a way to unite these problems in a meaningful way. And if that's the case, well, how can we reason about data structured as graphs using modern data-driven methods in the context of robotics? Now, my current hypothesis is that we can use the framework of message passing graph neural networks to tackle problems in these areas. And, this is a hypothesis because this is very recent work that we've been doing with state-of-the-art methods that keep evolving and are active sort of research problems on their own. But perhaps, it would enlighten you in terms of novel applications of these techniques in the context of robotics. And so what I'll do in the rest of this talk is I'll give you a very quick overview of how message passing graph neural networks work. And then I'll dive into some applications in the context of what I've talked about so far. And I'll tell you a little bit about new things that we've been doing to try to scale data collection for these problems. And so let me start with message passing GNNs. So we're going to be thinking about graphs. And so let me first formalize a graph in this context. We're going to have a global attribute which contextualizes information in that graph. We're also going to have a set of node attributes that tell us information, for instance, in the case of locations, maybe how this space looks like, or in the case of people, attributes over individuals. And we're also going to have edge attributes that are features that give us information about relationships in that graph. And so the way these graph neural networks are going to work is that they're going to use what is known as a graph network block to transform an input graph, all of its features, into another graph which has updated features. And this is typically going to happen in 3 steps. we're going to use neural networks to update the edge features. Then we're going to use neural networks to update the node features. And lastly, we're going to use neural networks to update the graph attributes. Now that these graph neural network blocks, they are composable. So you could have several layers of them, like you might have several convolutional neural layers in a CNN. All right. So with that very, very brief introduction, let me tell you about how we've used GNNs for navigation. Now, thinking about navigation in human environments, you're probably not thinking about graphs first. You're probably thinking about navigation with metric maps. Metric maps are like the one that the picture that you see here on the left, which is literally a grid of occupancy values where each cell has a particular dimension in the real world, which tells you very precisely, you know, which parts of the space are free to navigate versus occupied. Now, metric maps have been used forever. You can even encode in them information about perhaps social norms, like was done a long time ago with layered cost maps. More recently, though, people have started to use them to combine data-driven control algorithms with reasoning over this grid space. And so to give you an example, I'll talk about very briefly about the paper on the right, which is paper that we did in collaboration with Stanford. So here we want a robot to navigate in a metric map. The metric map is the background of this picture that you're seeing now. And we also have in the environment pedestrians and static obstacles that are not in the map. As you can see, they're not marked down in the background. Nonetheless, the robot has to be able to navigate around them. And so we want the robot to reach a goal. We know the robot's initial location when navigation starts. So we can compute a global plan on this metric map using, say, a start to figure out how the robot can go from where it is to this goal, ignoring all dynamic elements. And then what we're going to do is we're going to use machine learning to adapt that local plan. And the way we're going to do this is, well, two ways. First, we're going to predict a local plan for the robot, which is the blue line. And based on this local plan, the global plan, and the robot sensors, we're also going to predict velocity for the wheels of the robot to move. And so if things are working well, you should see the local plan adapting to elements in the map that are not represented statically, but that are seen by the robot sensors. And then you should be able to see the robot reaching its destination. And so I'm going to play this again. This was a little bit slower so that you could sort of pay more attention. I'm going to play it again a little bit faster so you can see it working a bit better. All right. So this worked. It showed us that we can actually effectively use these metric maps for navigation. But building these maps is often a lot of work. So normally you would have to scan the whole environment and make sure that things, you know, close very well nearby places that were scanning one point in time versus another point in time. And so given all these typical difficulties, we were thinking, well, do we really need a detailed metric map to navigate from one place to another? And part of this question comes because humans don't really have such a precise representation of the whole world, and yet very often they can navigate without too much trouble, right? And so how can we enable this type of reasoning for robots? And this is what actually got us thinking about navigating with topological maps. Topological maps being graphs that represent, you know, the topology of the environment in terms of key places where you need to make a decision as to where you're going to go, and then connectivity among places that tell you, you know, how you can get from one place to another. And so let me talk about this project where that's the key idea. How do we enable robots to navigate with this type of graphs? Now, in this problem, we're going to have, you know, a complex human environment like what you see here. This is scanned from a Stanford building. And our topological map, which we're going to assume is given, is going to have nodes for critical locations where you have to make decisions about where to go next, and edges that connect these locations. Now, the peculiarity of this map is that the edges not only tell you about traversability, but they also encode information about the type of behavior that the robot should execute to go from the source node to the next node. So for instance, let's say that the robot wanted to go from A to B, then the graph will tell the robot, oh, this edge means turn left, then follow the corridor, and then follow the corridor. And so what we're given to recap is this topological map, the initial robot location, a navigation plan, which is a path in the graph, which we can compute because we know initial location and where the robot wants to go, and current observations from the robot about the environment, like the depth image that you see on the bottom right. And what we want to do is, well, enable the robot to get, say, from A to B while following that path in the graph. So how do we do that? Well, there are two main challenges we need to solve. First, localization, and then control for actually moving the robot. And so this is where GNNs become key. We have a topological map. We're going to use GNNs to reason about where the robot is in this graph. And so we're going to start by setting up our global features for the graph using a CNN that computes a vector representation for an image stack of observations. Then we're going to crop the topological map around the location where the robot is. That's going to give us our set of nodes and edges. And we're going to provide features for them using an embedding lookup table. And then given this now graph that has node, edge, and global graph attributes, we're going to use the GNN to classify the edges such that we predict in which edge the robot is currently on. Now, this is something that is going to happen over time because the robot is going to be moving. And so we're going to pass our predictions to our next steps to redo the cropping so that we keep moving along the graph as the robot is moving. So for example, here you can see some predictions. In the top, you have what the robot was observing. Note that we were not using RGB images, we were using depth images instead, but for showing you what's going on, it's easier to see the RGB images. And then in the bottom, we have the prediction probabilities where darker means more likely, okay? And so the robot starts within the office, and so the bottom arrow is darker, and then as it starts moving towards the door and turning left, then you can see that the predictions start changing towards the left. All right. Now, we also need the robot to move, right? Not just to know where it is. And to do that, I mentioned before that the edges had a set of behaviors that could be executed. And so what we do is we train specific visual motor policies for each of these behaviors. So for instance, we're going to have a policy for turn left, another one for turn right, another one for finding door, and so on. Each of these policies, the key is that they're trained to avoid collisions, right? We want the robot to be able to do what it's supposed to do without sort of getting stuck in the environment. And so with these behaviors, given the localization information, what we can do is then switch between the behaviors to control the robot depending on the edge that it's on at a given time. And so the GNN will tell you, this is the edge where you're in. The navigation plan will tell you that edge corresponds to this behavior. And then we simply apply the velocities output by that visual motor controller to the robot to make it move. So how does this look in practice? Here's an example going from the room in the bottom left to the room in the top right. And it's quite great to see that you can compose these behaviors and actually achieve way more complex navigation paths than you would have out of any one of them. And this is all enabled because we're reasoning about the environment based on a topological map using graph neural networks. Note that all of the data that we created for this project is available. The data set that we published, which includes also semantic information like you saw on the bottom left, is all available. And so if you wanted to work on this type of problem, check out this project. I can provide you the link later. Now, this year, we also extended this line of work to reason about vision and language navigation, where the goal is, well, I not only want the robot to get to a given place, but I'm going to give the instructions to get to that place via natural language. Now, to do this, we decided to get rid of our handcrafted topological maps because it's actually a lot of work to build them. And we decided to make them using exploration. This implied that we didn't have those behaviors for the edges from the get-go, but instead, we wanted the robot to learn how to move from one node to another based on its observations. And so we ended up encoding in the nodes of the graph RGB panoramas of what was seen from that location. And then in the edges, we put information about the relative pose of one node to the other. Now, for figuring out how to move based on language, what we decided to do was try a cross-model transformer architecture, where the idea is that we want to ground the words that were given to a path in that topological map. So I'll give you a quick example here. Say that an instruction says, head forward past the kitchen and take the first left at the dining table. Then wait in the hallway between the living room and dining room. So if those are your instructions, what our model does is it associates the first left with our first set of nodes in our path. Then it associates the hallway with what is the hallway in the environment, and then it associates the living room with that part of the environment as well. Now, again, we want the robot to move, and so in this case, we decided to create a hierarchical controller that executes the plan. I won't go into the details of this controller, but I want to show you an example of it working in practice. So here you have a predicted path that the robot should follow. You have what the robot is seeing currently as a panorama, so there's a lot to see. And then at the bottom is the instructions that were given to the robot in this case. So I'm going to read the instructions and encourage you to focus in the top two images because there's a lot to see. Walk through the open doors and into the bedroom. Walk through the door on the other side of the bedroom past the bed and lamp. Walk through the hallway and turn the corner. Walk to the entrance of the home and stop in the doorway. So this is a very, very challenging task. I was quite surprised that this actually worked in practice by composing all these different techniques together. It's quite exciting to see, as I said before, that we can reason about these topological maps using GNNs these days. Now I'm going to switch gears and talk about interactions and how we can reason about them based on spatial formations. The motivation for this work was actually my PhD. So at the time, as you saw before, we have several situations where people that we expected to interact with the robot didn't quite do it. And our robot just didn't have a way to recognize that this was going on. And so we kept wondering, how can we enable robots to identify the members of their conversations? You may think, well, you can use audio, right? But what if the environment is a little bit noisy? What if audio is not quite certain? And our realization is that, well, perhaps robots can leverage spatial behavior, the way that people are moving, to identify these conversations that are happening nearby. And the reason why this is possible is because oftentimes when people converse with one another in open environments, they stand relative to one another in very repetitive and particular ways, like, the examples that you see on this slide. And these type of formations, they emerge because people not only need to be nearby to one another so that, you can hear what other people are saying, but they actually facilitate people watching other people so that they can check that information is being communicated as intended. And so, you might have people face to face, or maybe in an L-shaped formation, or maybe you might have people in more circular arrangements, because otherwise people won't be able to see each other if they're actually all part of a conversation. Now, in the context of robotics, prior work has shown that this type of formations emerge as well with robots like the ones you see here, including the one that I used for my PhD on the right. And this made us think, well, okay, let's try to detect these conversational formations in practice using, whatever sensors we can get out of a robot. How can we do that? And so I'll show you here one particular approach that I think is particularly promising. So what we're going to do is we're going to represent the social scene as a graph, where each person corresponds to a node, and each node at the bare minimum has information about people's position, which is X in this slide, and their body orientation, which is theta. Now, the edges of this graph, we're gonna have a weight associated to them, or an affinity value, which encodes the likelihood of those two people being part of a conversational group. And if we can build this affinity matrix, then we can go ahead and cluster groups using graph clustering techniques. Okay, and so that's sort of the big vision. Now, the big question to make this work is, what kind of affinity values should we use for those edges? How do we compute them? And so one idea is, well, we can use information about the features on the nodes connected to that edge. And these are, say, for an edge ij, the x and theta that correspond to I, and the x and theta that correspond to j. And indeed, prior work has shown that if you model this kind of problem this way using, say, a backtrees classifier, then you can generally do better than handcrafted approaches that try to do group detection using mathematical models of these formations. Now, when we start working on this problem, our realization is that, well, it's not just the people that are connected to that edge that matter, but actually everybody else around that edge tells you a little bit more information about what's going on. And so what we did was we augmented this function to include what we call social context, which are attributes of other people nearby that are passed as input to this model. And so we call this model DANTE for Deep Affinity Network for detecting these conversations. And the way it works is the network is going to have two main branches. The diet transform is going to compute a feature representation for the two nodes that are connected to the edge that you care about. And then the context transform is going to compute a feature representation for everybody else. And then we're going to combine these feature representations into an affinity value using, say, a multi-layer perceptron. Now, at the time, the key question was, how do we deal with the fact that we might have different people in different positions for this context transform? So what we ended up doing was treating this problem as if the inputs are a set, which indeed they are, making the network permutation invariant to its inputs. And the key here was using a symmetric mathematical operation for combining all the information coming from these different nodes. Nowadays, we know that this type of deep set architectures are actually a specialization of GNNs. And so later on, I'll talk a little bit more about that. Now, when we tried this out, the great thing that we saw was that adding this context information, which is the purple bar here on the right, actually improved all results. Here, higher is better. And these are results on a standard computer vision data set for group detection. Now, it was great to see that we can also deploy this model on a situated interaction with this robot that you see over here in our lab, where we were getting features from a Kinect that you see on the top. And so here, the red arrows correspond to the affinity predictions. Everybody's color based on the group that they're predicted to be part of. And here, there's no temporal information. So predictions are made on a frame by frame basis. And despite this, the results look quite stable over time, which is quite exciting in my opinion. Note that the robot in tiny there also has a small arrow because we're considering the robot as another social agent in this environment. And so, as I said before, these deep set architectures can be thought of as specialization of GNNs. And so this made us wonder, well, what if we try our full message passing GNN on this problem? And so we decided to try this out in a way more complicated data set than what we had tried before, which is the match and mingle data set that you see here. This is a hard data set because there's a lot of people around, and it is hardly seen this level of crowdedness in other cases. And so what we found here was that the more individual features we had for the people in this scene, so for instance, we went from position and visual features, which are the image features that you see on the bottom, to position, image plus acceleration, to position, image plus acceleration, and some activity labels. The more features we have, then the better the GNN tended to do in relation to our original DANTE model, where here, higher is better in terms of group detection. And to me, the reason why this is happening is because the GNN is actually better taking advantage of the relational inductive biases in that input graph that we have for this problem. Now, we have also recently tried the inverse problem. So given a group of people that we assume we know are part of a conversational interaction, where should we put a new member like a robot? And we tried to implement this in particular using a generative adversarial network because we wanted to model sort of the distribution of different options that new member might have to join a group. And I don't have to go into details, I don't have too much time, but I wanted to show you some results very quickly. So here at the top, we have the output of our GAN model. Then at the bottom, we have another method that we implemented that uses optimization based on hand-coded rules that describe the geometry of this type of formations. We thought first, oh, come on, these formations look simple, right? We can write down some rules to describe them. And what's happening here from left to right is that we start with one person in the group, which is in orange, then 2 people, then 3 people, and so on. And then our predictions are in purple, where darker purple means that's the final output that we're given, but then lighter purple is the distribution that we're modeling. And so as you can see, as you go from left to right, the predictions by our GAN tend to be way more consistent with the properties that I described before early in this presentation. Whereas our geometric model eventually doesn't even look like a circle at all in the sort of rightmost slide. And even more, it actually puts people on a different room than everybody else, because the way that it's reasoning about space is very simplistic based on the rules that we could come up with when we implemented this. Whereas, you know, the GAN actually can reason about space in a way more coherent way and everything else for this type of problem. So that was actually quite exciting. Now, making all of these systems work, as you probably can guess, requires a lot of data. And so getting data in human-robot interaction is very expensive, right? Because it typically entails in-person user studies and things like that take a lot of time to run. And so what we've been thinking about lately is, well, how can we scale data collection? And for that, we've jumped into the simulation world, and we built an environment called the Social Environment for Autonomous Navigation, which is built on Unity. And from the get-go, it gives you access to exporting information to the robot operating system, such that hopefully you can do sim-to-real transfer in a practical matter if you're using this type of simulator. Now, I don't have time to go into the details of the simulator, but I want to tell you the punchline, which is the latest things we've done. And that is to take this simulator and deploy it on Amazon Web Services, such that a user can actually access the simulation through a regular web browser without needing to have specialized hardware to run all the fancy graphics that are happening on the cloud. Now, what can you do with that? Well, if you can suddenly deploy these simulations on a regular web browser, you can embed them into surveys that you can use to crowdsource human-robot interaction experiments at scale. So for instance, right, we can have a survey where there's an embedded simulation, and we might ask people, hey, I want you to move this person, this avatar, from one place to another. And then after they do that, after they've seen the robot in the simulation, we can ask them a bunch of questions that you would typically do in a user experiment. What do you think about the robot of the motion when you pass nearby it? Did the robot react naturally to you? And then in the back end, right, we can have that robot being controlled by the same code that in practice will be running on the physical robot, because we have connectivity to the robot operating system, which is what we typically use to control our robots. And so just to, you know, give you a very brief overview of how this works, you know, we can have a person controlling a human, and there are important questions here, you know, like even what viewpoint you should give that person. But nonetheless, you can have a person controlling a human and then ask them to complete questions in the survey as you see fit. These days, we're also thinking of, you know, having people control the robot, and perhaps even thinking about what a multi-user version of this might look like in the near future. And so with that, I want to thank all the many students that have made this possible. This is really their work, not so much my own. And I want to thank also our sponsors for supporting all of our efforts. And I'll end by reiterating sort of the main idea of the work that I presented today, and that is that GNNs are very exciting models. They provide novel opportunities to bridge problems in robot mobility and social interaction analysis in HRI. And perhaps we can do even more with them in the context of robotics in the future. And so if you want to learn more about sort of all of these different projects that I presented, all the links to the project websites and the papers, they're all available in our lab link that you see here, interactive-machines.com. And I want to invite you to the Q&A to, have a chat and a discussion about any of this if it sounds interesting to you. And so thank you for listening today.
Okay, well, thanks again. Thank you, Marynel. Apologies, first of all, because I went straight into the presentation without giving you an introduction. So for everyone, I posted Marynel's Dr. Vázquez's bio in our Rocket chat. And so now that we're entering our Q&A session, so we do have a question that came up on Rocket chat. So this is from Albert Orozco Camacho. He says, hola, I've got some questions for Dr. Marynel. How many people are usually involved in the post-test interaction experiments? And is there a limit for the proposed GAN model to work well?
Oh, I'm not sure I follow the first question. How many people are involved in the post-interaction experiments? So I'm not sure what you're asking about, but I'm going to make some guesses. So if you're thinking about the work with Sean with our simulator, right now there's only one person that can interact with the simulation, and that person is the one person that fills out the survey, whatever questions we're asking. However, in the simulation, we have other avatars moving around using state-of-the-art crowd simulation algorithms. And so there might be other people that perhaps interact with the avatar for that one user. If you're thinking about perhaps experiments where we test out robots in the real world, well, the amount of people that you might get is a function of both how busy that environment is from the beginning and how many people you can recruit to actually help you out during your test. So oftentimes what might happen is that, say you want to test your robot in one place, but not many people come along, then it's really hard to have your robot running for many, many hours. And so you'd rather try to encourage people to, hey, come to this place, and how many people you can get to go there to test out what's happening, might give you a hint as to how well things are working. Of course, that is not as good as you suddenly driving your robot out in the real world. And then in the real world, if you go for that, it really depends on how many people are around. Now, there was a second part to the question.
Yes, is there a limit for the proposed GAN model to work well?
So I believe the answer is yes, and the answer depends on the distribution of the training data. So when we train the model, we first try to use data sets from computer vision that had realistic groups annotated in them. However, these data sets tend to be really small. And so that didn't work very well with our GAN, even with the smaller set of parameters we could set into our GAN. And so then we said, well, you know what? We know a lot about these formations. We can actually model groups with very simple rules, kind of like what we were doing for our other geometric baseline. And what we can do is, once we have these groups, we can actually deform them and apply a lot of transformations to make them a little bit more varied. And so we ended up doing this for groups from sizes 1 to 6, because the main data set that we were using from computer vision had groups of those sizes. And in general, that worked out really well. Now, testing a machine learning model that you tested on groups from 1 to 6 on a group of, say, 9 people, that seems risky. And so we ended up doing that as part of our experiments to see how well it worked. And I can report that at least up to 9, things started to deviate a little bit, but we're not too crazy. I think that if you go beyond that, it'll definitely not work very well. And all that boils down to the type of data that you're using to train your model. I think that if you had data that had groups with many, many people, I think the GAN will figure it out eventually and work well.
Excellent, thank you. So I actually had 3 questions for you. I don't see anybody else posting, yeah. So we still have a few minutes. You mentioned Unity as one of the game engines. I actually work there, and I do a lot in the simulation world. So Synterreal is one of the things that is of interest to me. I work in the RL space. So my first question is, considering your last response to the GAN question, have you considered using Unity or some other type of engine to generate synthetic data to augment your computer vision data sets?
Yes, we're doing that.
Okay,
so
excellent.
Yeah. So the simulator that I talked about, where we have, people putting around and we can put a robot, we're definitely trying out, what if we have an RGB camera there? What if we have a depth camera there? What if we have a LiDAR there? And then we use this environment to get lots and lots of example data from which we can train models for navigation. We're also thinking about problems of, how do we now translate some of these sort of group interaction ideas to the context of the simulator. And that way we can hopefully make, the navigation type of scenarios that we can study more diverse than what you would typically get if you just have kind of random people moving around the environment from one place to another. And so I think, I'm very excited about Unity, and there's lots of amazing things that you can do these days with sort of state-of-the-art graphics and all of the hard work that has come into making this kind of a usable tool for anybody, which is also why we went for Unity. And yeah, I just see possibilities of cool things we can try out with that. Now, I must admit, there is one big challenge still, in my opinion, in terms of scene to real transfer, and that is dynamics. So, like things, you can make them look fairly realistic. And if you're using sensors where, even like a depth camera, you add some noise, perhaps it kind of works okay in the real world. But in terms of like the actual motion of the robot, getting those parameters down to transfer very well, that's actually something that we found to be quite challenging. And if you think about people, on the other hand, if you think about the dynamics of people in relation to other people and in relation to robots, that's something that I think is an open question. And so, there's lots more to be done in that space.
Thank you. So I can just tell you that we're working on all of those problems internally.
Sounds awesome. So we should be talking more.
Yeah, definitely. More to come soon. And so on that note, I think we have about 5 minutes left. Let me check if anybody else has any other questions. If not, I can unload another question. No questions so far? Okay, so I do have one on the crowdsource piece, because that's another thing that we are exploring, because we're working on trying to use in simulation to generate more human-like behaviors through training. So we're trying to, one of our goals is to try to create trained policies that sort of behave the way humans do. And so this idea came up on sort of how can we get and record trajectories that are driven by humans, and not just like, our team kind of sitting there and playing the game and going through the motion, right? So if you could talk a little bit about maybe the ethical implications of that, because this is something that sort of came up. We're gathering data from humans, and so there's all sorts of things that kind of arise there. And if you've given any thought to the ethical implications of the data collection via this type of sort of web-based simulation interface. Yeah,
so we have we do a lot of user studies all the time for in-lab experiments that we do and things like that. And so we're all very well trained on sort of going through the standard procedure of getting institutional review board approval, creating a consent form, and following sort of standard practices to make sure that the data is safely protected and so on. And so all of that actually can transfer very easily to the crowdsourced world, because you can present people a consent form at the very beginning of your survey that says, hey, this is a study and this is how we're going to use your data. Do you agree to participate on this and record your data, yes or no? And it's up to them to decide, right, whether or not they actually want to give us that data. And so there's not so much trouble there. What I think is a little bit more tricky from an ethical standpoint is assuming that the models that you train in simulation would automatically transfer to the real world. And the reason why I'm saying this is because people don't necessarily perceive a robot the exact same way they would in the simulation as they would in the real world, which means that the data that you might get, the trajectories, might not actually be representative of the type of distribution you might get if you had asked people to give you trajectories in the real world. And so you have to be really careful about that deployment later on, because out of distribution samples are a big problem for machine learning today. Does that make sense? And so that is, to me, I think the biggest challenge from that. And there's very, very simple things that will make a humongous difference in terms of the type of data you get. Things like, what viewpoint do you give users? What controls do you give them to be able to give you a trajectory? Are they using a keyboard? Are they using another type of input modality? There's lots and lots of open questions in this regard that we're barely, you know, kind of scratching the surface right now with what we have, but I think are going to be really meaningful for making sure that the data you're getting is representative of what you would get, you know, in the real world. This is actually one of the reasons why we modeled our laboratory for Sean. So we have a 3D model of our lab such that we can test, oh, what if this, you know, data that we get in our virtual lab, how would that work in the real world? But we don't know yet. This is something that we have yet to do.
Yeah, thank you. That was an excellent answer. And we're also working on that same problem in trying to figure out and match distributions and supports for those distributions that you'd find in the real world in synthetic data. So it's an open question, open problem, but we have a team internally here that's working on those very questions. So
that sounds great. We should be talking more.
Yeah, definitely.